I'm fitting a model using Sklearn's LarsCV, which uses least angle regression and cross-validation to find the best model. It's like trying different combinations of ingredients, features, to make the best cake, model, and cross-validation is like testing each cake on different groups of people, data subsets, to see which one is the most popular. LarsCV is the algorithm I'm using. The CV equals 5 inches part means I'm using 5-fold cross-validation. This is like dividing my cake testers into 5 groups, each group trying a different version of the cake. I have 1,000 samples of data, each with 100 different features. Think of each sample as one person's responses to a survey with 100 questions. My data is split into 5 folds. In each round, 4 folds are used for training and 1 fold is used for validation. I then do this process 5 times, rotating which fold is the validation fold each time. It's like testing 5 different cake versions on 5 different groups. The best one wins. LarsCV automatically chooses the best, alpha, value, which controls the amount of regularization. Regularization helps avoid overfitting. It's like finding the perfect amount of sugar and flour. Too much or too little and the cake won't be great. Alpha helps me find the just right amount of features. LarsCV automatically chooses the best number of features. It does so by picking the best alpha that produced the lowest error based on my cross-validation testing. It's like finding the perfect combination of ingredients, not too many, not too few, just the right amount to create the best cake. After the cross-validation, I have a final model that uses the optimal number of features and the best alpha value. It's the winning cake recipe from my 5 taste tests. Delicious. This tells me we're working with a dataset containing 1,000 samples, each described by 100 features. Think of each sample as a data point and each feature as a characteristic describing that point. For example, imagine analyzing customer data. Each customer is a sample, and features could be age, income, and purchase history. Here, CV equals 5 means I'm using 5-fold cross-validation. I divide the dataset into 5 equal parts. In each iteration of the process, 4 parts will be used for training the model, and the remaining part is used for validation. This helps to prevent overfitting and gives me a more reliable estimate of the model's performance. This step involves randomly dividing the 1,000 samples into 5 folds. Each fold contains 200 samples, 1,000 samples, 5 folds equals 200 samples, fold. LarsCV, my least angle regression with cross-validation model, will use this step to find the best alpha. Alpha is a regularization parameter that helps prevent overfitting. It controls the strength of the penalty term in lasso regression, which indirectly impacts the number of features the model uses. I search for the alpha that minimizes the error across all my 5 folds. Once I've determined the best alpha, I automatically get the best model. This model includes only the most relevant features, eliminating those that don't contribute significantly to the prediction accuracy, and it happens implicitly because the alpha value determines the optimal number of features selected. Cool, right? I'm fitting a model using Sklearn's LarsCV. LarsCV stands for Least Angle Regression with Cross-Validation. It's a powerful tool to find the best model for prediction. I'm setting the CV parameter to 5. This means I'll use 5-fold cross-validation. That is, I divide my data into 5 chunks, train my model on 4, and test it on the remaining 1. I repeat this process 5 times, each time using a different chunk as the test set. This helps me avoid overfitting and get a better sense of how well the model generalizes to unseen data. I have a dataset with 100 different characteristics, features, and 1,000 individual examples, samples. That is the data I'm using to train my LarsCV model. I'm using 5-fold cross-validation. That's my method to evaluate my model's performance. I divide my data into 5 equal parts. I train the model on 4 parts and test it on the remaining part. I repeat this process 5 times, each time using a different part for testing. The results are then averaged to get a reliable estimate of the model's performance. I'm implicitly using lasso regularization. Lasso helps prevent overfitting by shrinking the coefficients of less important features towards 0. The regularization path refers to the sequence of models generated as the regularization parameter, alpha, changes. Alpha controls the strength of the regularization. I'm using cross-validation to find the best value of alpha that minimizes my prediction error across all folds. This is my most important parameter selection. By selecting the optimal alpha, I indirectly select the optimal number of features. Lasso automatically eliminates features with smaller coefficients, those deemed less important. After finding the best alpha through cross-validation, I obtain the best model, which uses only the most important features and has the lowest prediction error. This is the final model, ready for deployment. I'm using Sklearn's LarsCV, which is a fancy way of saying least angle regression with cross-validation, to create a model. It's like a super-powered regression that uses a clever technique to find the best features for the model. The "CV" parameter is set to 5, meaning I'll split my data into 5 different groups. I'll train my model on 4 of those groups and test it on the remaining one. I'll repeat this process 5 times, each time using a different group as the testing group. This helps me get a reliable estimate of how well my model will perform on unseen data. I have a dataset with 1,000 samples and each sample has 100 different characteristics. I want to create a model that can predict some outcome from these 100 features. Least angle regression, LAR, is the core algorithm used by LarsCV. It's an efficient way to fit linear models, especially when dealing with many features. Think of it as a smart way to find the best combination of features that explain the outcome, kind of like carefully choosing ingredients for a perfect dish. LarsCV uses cross-validation to automatically find the best value for alpha, which is a parameter that controls the complexity of the model. It's like adjusting the seasoning of the dish. A small alpha means the model can be very complex, and a large alpha simplifies it to avoid overfitting. LarsCV finds the sweet spot alpha that generalizes best to new data. I'll train the model multiple times using the 5 different folds to find the parameters that yield the best cross-validated performance. I'm evaluating how well the model performs on each of the test sets to prevent overfitting and get a robust prediction. During the process, the optimal number of features to include in the model is automatically chosen. It's like deciding which ingredients truly contribute to the best flavor. The choice is informed by the performance across the 5 test sets to find the best compromise between accuracy and simplicity. After the cross-validation, I'll get the final model with the best alpha value, which implicitly determines the best number of features, ready to make predictions on new, unseen data. It's like having the recipe for the perfect dish, using just the right ingredients. I'm fitting a single least angle regression model using the LarsCV function from Sklearn. This isn't multiple separate models, it's one model that I evaluate multiple times using cross-validation. I split the dataset into 5 equally sized subsets. Each subset will take a turn being the test set, while the other 4 are used for training in each of the 5 iterations. This is the first iteration. I use 4 folds for training and 1 for testing. I will evaluate the model's performance on this test set. Next iteration, a different fold serves as the test set now, and I again evaluate the model's performance. I continue this for all 5 folds. Iteration 3 uses a 3rd fold for testing, keeping the process the same. Iteration 4 is similar. A new test set is used. In the final iteration, the last fold is used as the test set. I fit one least angle regression model in each fold. The model is fit to the training data and evaluated on the test data to find the best regularization parameter alpha. I calculate the error, likely mean squared error, of my model on each test set and compute an average across the folds. This average helps me find the best alpha. Based on the average cross-validated error, I select the best regularization parameter, alpha. Alpha helps control the complexity of the model, indirectly selecting the number of features. I refit the model using the entire dataset and the optimal alpha that I found during cross-validation. This gives me my final model with the optimal number of features. It's crucial to understand that I only train 1 LAR model. The cross-validation process is used to evaluate its performance and select the best regularization parameter for this single model, not to train several separate models. I'm using Sklearn's LarsCV, a cool algorithm that combines least angle regression with cross-validation to build a predictive model. It's like a smart shopper choosing the best ingredients, features, for a delicious recipe model. The CV parameter in LarsCV sets the number of folds for cross-validation to 5. This means I'll split my data into 5 groups to train and test the model, making sure the model generalizes well to unseen data. Think of it like testing a recipe 5 times with slightly different ingredients each time to ensure its consistent deliciousness. I'm using 5-fold cross-validation. This means I split the dataset into 5 equal parts. I train the model on 4 parts and validate it on the remaining part. I repeat this process 5 times, each time using a different part for validation. This helps me evaluate the model's performance reliably. After the cross-validation, I evaluate my model's performance using a measure like the least squares error. Based on this evaluation, I select the best value for alpha, which controls the amount of regularization, lasso in this case. A lower alpha means less regularization, more features, and higher alpha means more regularization, fewer features. It's like finding the perfect amount of spice to make the dish amazing. The best alpha value implicitly determines the number of features included in the final model. LarsCV automatically selects the optimal number of features during this process, so I don't have to manually choose them. It's like the algorithm automatically figures out which ingredients are essential and which are not. My dataset has 100 features, potential ingredients, and 1,000 samples, recipes to learn from. Each sample has 100 feature values representing different ingredient quantities. I'm using 5-fold cross-validation, which means I divide the dataset into 5 equal parts. I train the model on 4 parts and test it on the remaining part. I repeat this process 5 times, each time using a different part as the test set. This gives me a more robust estimate of how well my model will generalize to unseen data. This is like testing different sections of the dataset before using the entire dataset to ensure accuracy and that the model works across all similar datasets. LarsCV stands for Least Angle Regression with Cross-Validation. It's a technique I use to find the best linear model for your data while also selecting important features. The cross-validation part is key. It helps prevent overfitting by testing the model's performance on different subsets of the data. The dataset I'm working with has 1,000 rows, samples, and 100 columns, features. Each row represents a data point, and each column represents a different characteristic or variable. It's like having 1,000 students, and 100 pieces of information on each of them, like age, grade, etc. The regularization parameter, often called alpha, controls how much I shrink the coefficients of my model towards 0. This prevents overfitting by keeping the model simple. I use cross-validation to find the best value of alpha that balances model complexity and prediction accuracy. Think of it like finding the sweet spot to adjust the learning of your model so it generalizes well. Once I have found the best alpha, I've also implicitly determined the optimal number of features for my model. Features with small coefficients will be essentially ignored, automatically leading to feature selection. This is like automatically selecting the most influential factors that explain the result. For example, if I'm trying to predict student performance, age may be less important than study hours. Although I'm not fitting separate models for each fold in cross-validation, I am using linear regression models multiple times during the cross-validation process to find the best alpha and implicitly selecting features. Think of this as doing multiple trial runs with slight adjustments to ensure the best possible model is found.